today's class we look at indexes in databases. What do you mean by an index? An index is an optional structure associated with a table. And why we use an index is to speed up your data access from your disks. An index is an optional structure. It's not mandatory. You need to have an index to retrieve data or manipulate data on a table. But when you have an index, the chances are you will speed up data access, and this is one of the means for reducing disk IO. So let us go and look at what happens we don't have an index, and then we'll see how index improves the performance of our data retrieval. So we'll take a scenario here. Let's say this is our hard disk, a large hard disk I put up there, and on this hard disk I have an employee table. An employee table divided into many blocks. Say this table is very large, and each block, say it's of 1024 bytes. So my employee table is divided, or is partitioned into many blocks. So all these blocks contain my employee data. So when you take a look at this organization of the file here, it is all organized using an ordering key. So what is an ordering key? I organize my data using that key. Here the key is employee ID. So you take a look at the employee ID. All the records are in the ascending order of the employee ID. So I maintain such an organization internally on a file on my hard disk. So what is the advantage of this kind of an organization? What is the disadvantage of this kind of an organization? Say I'm ordering all the records using an ordering key inside internally on my data file. So what is the advantage of this? Say I want to do a query like this. Bring me all the employees whose employee ID fall between 111 and 115. So in that case, all the employee IDs are very well organized together. I can go to one block and retrieve all that together. Range queries can be very effective here. And what are the problems in maintaining an organization like this? I told you one of the advantages. Is there any problem in maintaining an organization like this? Say if I want to insert a record, and that record should be inserted somewhere in between. So what you have to do, you have to move all the records. There's a movement of records associated with maintenance of this kind of a file. If I delete one of the records or two records from a block, then what I should do? I should be moving records so that I have to conserve space. And the advantage of this is reading is very fast. When you're reading data in an organized fashion, it will be very fast. Whereas writing will be slow because you have to find a slot to insert that, and then you have to move records. So I am organizing my employee data like this, and now say I want to run a query. Give me the data of employees whose ID is 121. I want to run this query. So how the search happens on my file? Let's consider a linear search. What do you mean by a linear search? You would have learned that in your previous year courses, right? So you start from the very first record, you search record by record to see whether there is a match. So you start with 111, 111 is not matching with 121, so you go to the next record, you go to the next record, you keep on searching until you get a match for your, for your search. So this is a linear search, and what are the disadvantages of a linear search? How many comparisons you have to make on an average? I'm not talking about the worst case. On an average, how many comparisons you will make? So now on an average for any search, when you're performing linear search, you'll make n by 2 comparisons. So the same thing applies here. When I'm going to apply linear search on all my blocks, on an average, I should be performing b by 2 comparisons. That is, b is the number of blocks by 2. So I have to access b by 2 number of blocks to achieve a result on an average. Let's take an example. Let's say that my employee table contains 3000 blocks. You say that this employee table like this is having 3000 blocks. It's a very huge table. I've shown only 3 blocks here. Consider 3000 blocks from my employee table. So if I apply linear search, how many blocks I should access here on an average? On an average, you should access 1500 blocks. because 3000 blocks is the number of blocks, by 2 will be 1500. So what it means is when you perform linear search on a very large table, the number of blocks that you have to access also will be huge on an average case. Okay. So you have learnt about one more type of search, that is binary search. In what way you think binary search is better than linear search? And when will you go in for a binary search? So what is binary search? At every iteration, you're going to eliminate almost 50% of the records. So that improves your performance. So when you talk about binary search, the average number of blocks you have to access while using binary search is log b to the base 2. And when you apply binary search, what is a very important condition to have binary search? The data set should be sorted. So sorting is the most important criteria. Since we have already sorted our entire employee table using our ordering key, it's already sorted, I can very well apply binary search on my data file. So when I apply binary search on 3000 blocks of data, so what is that I'm going to get? The average access. So it's nothing but block B, number of blocks, log to the base 2. So that gives me 12 blocks. So I'll be able to reach to my result on an average access of 12 blocks. So what it means, when I use a linear search on this data file, I have to access 1500 blocks. You know what do you mean by accessing 1500 blocks? There is a disk seek time and a latency time and a block transfer time associated with every block transfer. So 1500 blocks will be really taking a lot of time. But when you go in for a binary search on the same file that is organized using an ordering key, the number of blocks is reduced to 12. So this is where we find an advantage, but then even this is a problem. When my employee table, say it is having 300,000 blocks, and my employee table is very large, the number of blocks I have to access using binary search also will be very large. So then our problem still remains how to reduce the search time. Even with binary search on a large table, the number of blocks becomes large. So how to reduce the search time? That is the question we have. And for that, the answer is, so this is the question, how to reduce the search time for large tables with millions of records. See, a table can run into many gigabytes. So in that case, your number of blocks will be very huge. Even when you apply binary search, it may take more time. So in that case, what is the answer to all these things? Create a primary index. So we are going to create another structure which will help us to speed up our retrieval. And I say this to be the primary index, one type of index. So for a primary index, the very first condition is your file should be organized or ordered using an ordering key. The ordering key here is employee ID. Okay. That is the very first important condition. Once when you have that, you're going to go and create another file that is called the index. This file will contain two fields, and one field is a pointer to the block on the disk. And where this file will be, this file also will be on your hard disk only. This will be maintained in your system dictionary file. It's a system dictionary file. So it will be part of your dictionary. You know what the dictionary is, right, in your database management system. So this file will also be part of your hard disk one. It will be stored on the hard disk, and what it contains, a pointer to every block. How many blocks you have here? 3 blocks. So there will be a pointer to every block. So the number of entries in this will be the number of blocks you have. And what is this? Every record will have a pointer to a disk block. So that's what it means. And what do you mean by this field here? The field there is nothing but you go to the block, go to the first record, take this value, give it an entry here. You go to the next block, the value of the ordering key in the very first record will be moved to your index. Likewise, in this block, the very first record, the ordering key value will be moved to your index. And this file, you call that to be an index file. The index file will also be in your dictionary, and when your instance gets created, will be used up by your Oracle instance. Okay. You understood what is this primary index? Okay. So every record will contain the primary key field for the first record in the block. See, otherwise employee ID I can say is the primary key also. So using the primary key I created an index and I take the first record from every block, take that ordering key, put that in my index. So that becomes my primary index. So what this kind of an index is called? Primary index. Okay. So some terms and terminologies from your books. A primary index is an ordered file. See, you have to understand that the primary index is also an ordered file. See, it is ordered in the ascending order. 111, 115, 119. So it's also ordered. Whose records are of fixed length with two fields. The first field is the primary key field of your file, and the second field will have a pointer to the block containing the record with the primary key. So the second field is nothing but it's actually a pointer pointing to the actual record on the disk, actual block on the disk. The total number of entries in the disk is equal to the number of disk block. So in your primary key index, I mean in your primary index, how many entries you'll have here? It depends on the total number of blocks you have. Please have these things in mind. Don't forget these things. So now we have created an index. How index improves our performance? That is the question. Will this index really be better than our binary search directly on the data file? So that is the question. So for that, we are going to take up a problem now. We are going to take some numbers here. I want you to note down these numbers and give me the answers. Let us consider an employee table containing how many records? 30,000 records. These are the actual records on the blocks. And let us consider every block can hold how many bytes? 1024 bytes. That is the block size. And what is the length of every employee record? Say there are 30,000 records. The length of every employee record is assumed to be 100 bytes. Now the question is, how many records can fit in a block? One record is 100 bytes. A block size is 1024 bytes. How many records can fit inside one block? Very easy, right? So it's nothing but the block size divided by the record size. So you can fit 10 records per block. Okay. So 10 records per block you can fit. Now the next question is, how many blocks required to hold 30,000 records? 10 records in one block. How many blocks required to hold 30,000 records? So it is 30,000 records by 10. That is, we need 3,000 blocks to actually hold a record size of, to actually hold 30,000 records in our tables. We need how many blocks? 3,000 blocks, provided each block can hold 10 records. And the record size is 100 bytes. Okay. So I have 3,000 blocks in my data file, the actual table. If I do a binary search, how many blocks I should access on an average? What is that? Log 3000 base 2. So when I do a binary search directly on the data file, how many blocks I should access? It is nothing but log base 2 3000. That is the number of blocks. So you have to access on an average 12 blocks to get your result. This is directly on the data file on your database without using an index. Is that clear? Now the question is, using an index, we'll create a primary index. We'll see how index improves the performance. So let us talk about index. When you talk about index, you have an index entry, right? What are the two fields? One is the primary key, another one is the pointer. We'll assume some sizes here. That is For my primary key, I give 9 bytes. For my pointer, I give 6 bytes. The size of my index is 15 bytes. So that's what is given here. For every record in my index file, it's 15 bytes. A block can hold 1024 bytes. See, it's common, right? For index or anything, the block will always hold 1024 bytes. Now, in every block, how many index entries I can have? The size of an index entry is 15 bytes. The size of a block is 1024. In every block, how many index entries I can have? It's nothing but 1024 by 15, 68 records you can have in your blocks. Okay. So how many total number of records you'll have in your index? How many blocks you had in your data file earlier? You did this, right? How many blocks you identified in your actual data file? 3000 blocks. So how many records you are going to have in your index file here? See, the actual database, it contains how many blocks? 3000 blocks. And you have created an index file which can, we have created a block which can hold 68 index entries. But how many index entries should be there in your primary index? There should be a pointer to every block in your data file. So there should be how many entries? 3000 entries. To hold 3000 entries, how many blocks you need? To hold 3000 entries of your index entries, how many blocks you need? Have I really confused you a lot? Let me go and again clear this. Let me tell you, it's very simple. Say you have an index file. For an index file, you have two fields. That is, one is the primary key, another one is the pointer. For the primary key, I have assigned 9 bytes. For the pointer, 6 bytes. So length of the index entry is how many bytes? 15 bytes. Block size is 1024 bytes. So in a block, how many index entries I can have? 1024 by 15. So that is 68 entries in a block. So I am holding 68 entries in one block in my index structure. This is the index structure. Whereas when you talk about the actual database, how many blocks are there in the database? You can think about 3000 blocks. That's what we have identified. So now according to our primary index concept, how many entries should be there? There should be an entry for every block. So and the index should hold totally 3000 entries. But a block can hold only 68 entries. So how many blocks we require to really hold 3000 entries? It's very simple, 3000 by 68. So you need 45 blocks to create your index. I told you index also is on your hard disk. So it's also held in a block. So how many index blocks you need? 45 blocks to hold your index alone. So when you do a binary search on 45 blocks, see your index file is also ordered. You do a binary search on your index. So what is the average number of blocks you have to access here when you use the index file? It is nothing but log 45 base 2. Log 45 base 2 will give you how many accesses? 6 accesses. But that is not enough. You just used your index file, you did your binary search, you went through to that particular block holding your pointer. Then you have to go to that actual block on the data file. So that is one more block access. So it is actually 6 plus 1, 7 block accesses. Earlier, without the index file, directly running your binary search on the data file, you are actually doing how many block accesses? It's log 3000 base 2, that is 12 block accesses. When used an index file, the number of block accesses reduced by 5. So what we understand here is an index file improves performance, reduces the number of blocks that you need to retrieve. The only thing is the primary index is also an ordered file. You can do binary search on the primary index. Then when you locate the block on the data file, that is one more block access. That's why I do 6 plus 1. So this example is from your textbook, Fundamentals of Database Management System. So what are the advantages when I use an index for searching? See, the data file is very large. It's 100 bytes, whereas an index file is only 15 bytes for each record. So you can very well search faster on the index file. And one more thing, a binary search on the index file requires few block accesses than a binary search on the data file. Data file will have 3000 blocks, binary search will be more taking more number of blocks, and index will have less number of blocks. So binary search will lead to less number of block accesses. Very simple. So this is the final thing. If primary index contains B blocks, to access a record using binary search on the index and access a record containing that block requires log to B plus 1 access. This plus 1 access is for going to the data file, accessing the data on that particular block. What are the problems with primary index? The primary index is also an ordered file. So when I insert a record in my actual data file, my index also should be modified. If I delete a record in my data file, my index also should be modified. Another issue is for my index also I should allocate some storage. See, if my actual data takes 3000 blocks, my index will take 45 blocks. So index also uses up some storage. So these are the problems associated with an index called primary index. Why we say it's a primary index? Because we can say it's built on the primary key, or it's built on a key that is used for ordering your files internally. We'll look at one more terminology, the sparse index. What do you mean by a sparse index? We'll take the same example you have seen. We have built this primary index, right? So you see here, there is an entry only for some of the values here. If you talk about the search values, these are the search values. Whereas in an index file, you have entry for only some of the search values. So such kind of an index is also called a sparse index. I have 3000 search values in my employee table, but I built an index containing only some of the values. So you term such an index as a sparse index. Are you all clear with this primary index and what is a sparse index? How binary search on a data file is no better than binary search on an index? Okay. Now you can ask me one question. Will the search always be on the ordered key? Will I always say select star from employee where ID is equal to 121? See, you take a look at this employee record here. I have 111, that is the employee ID, name, SAM, department is scope. This is the SSN field. Social security number, shortened for easy reading. So social security number is also an unique field for every employee. And why can't I do this query, right? Select star from employee table where SSN is equal to 249. Now I'm not using the ordering key, the primary key. I'm using an non-indexed field. Now how will be the search? I'm using a non-indexed field. You understood this? What I am using here, I'm now doing my search on this field. Bring me the employee with SSN, some SSN I have given there, 249. That is the non-index field. We don't have an index created for this field. Now, how will be the search? Can the primary index be used for this? We already built a primary index. Can we use that? No, because that is based on employee ID. That is of no use to us here. SSN is something that is not ordered. Why you say data is not ordered on SSN field? I say here data is not ordered on SSN field because you can take a look at this. It is not sorted on the SSN field. So what is that? The problem here is we can't use the primary index we have already created. So then how to search? Primary index is obsolete for this query. So how to search? A difficult question. How to search? Obviously, I should go in for a linear search. Why I should go in for a linear search here? Because you see here, the data is not sorted. So when I search here, I can't use binary search on this directly on the data file. So I should go with a linear search. So when you're going with a linear search, when there are 3000 blocks, how many blocks you should access? On an average, you should access 1500 blocks. Again, we end up with this problem. Just because the user searched it on some other field, again the performance become a problem. So that's what I have given here. Linear search is used since it's unordered, and the number of blocks you have to access is 1500 blocks. So in the industry, what they do is they know what are the fields used for frequently querying the database. See whether it's employee ID, SSN, they understand the user's behavior. So even before implementing it and making it available for the user, they'll create indexes on those key fields. So there can be many indexes existing in one table. That's what I mean to say. And how they identify that an index should be created for this field based on the usage patterns of your user or based on the knowledge they gain from the domain. Okay. So when you talk about VTOP or VIT, normally we use registration number. So that should be the primary key. An index will be built on the primary key. If we use your mobile phone that is unique for every student and it is not null, then I can also build an index for your mobile phone. And I will not be building indexes on something that I am not frequently accessing, because I told you maintaining index is also a problem. We have to modify the indexes, allocate storage for the indexes, we have to create indexes. So that's also an issue. So now the question is, I am accessing 1500 blocks here on a non-index field. Can I really improve my performance here? How to improve the performance here? So let us take this. We have already built a primary key index. I mean, we have already built a primary index. The answer to this is you create another index for this field, SSN field. And you're seeing here, that is the index, second index I'm creating. And this index will contain every value in your SSN. If there are 12 employees here, I have almost put all the values here. A secondary index is nothing but it's going to contain every entry as the field, and then you'll have a pointer to every record. See, you can ask me a question, why not an entry like this? Why you have to put every entry here? See here, if I want to search for record 112, what I can do is, I know this is 111, so I can go to this particular block and linearly search 112. That is possible. If I want to have a same kind of setup for an unordered thing, can I achieve that? Say I can go to 252, but I can't go to 253. You can't perform a linear search because that is unordered. So that is why we should have every entry here to be present in your index structure, because it's unordered and it will be scattered across different blocks. So you'll have a pointer to every record. So these are record pointers. So you see here, there will be a pointer to every record in your blocks. It's not a block pointer, it's a record pointer. And this type of an index, you call that to be a secondary index. Why I say it's a secondary index? Because it's an alternate way of accessing your data file. You're providing another means of accessing your data file. So let's go and take a look at certain terminologies. A secondary index provides a secondary means of accessing a file for which the primary access already exists. Already we have an index on the primary key. Now we have created an index on the SSN, that is the alternate key. The secondary index is an ordered file with two fields. See, this is very important. The actual organization of the data is unordered, but the index itself is ordered. So you create an index and you order it. And one more important thing, this should contain every search key here should be present here. First field is an index field on a non-ordering field, and the second field is a record pointer. So now the question is, will a secondary index really improve the performance? Will it be better than a linear search? So we'll take this simple problem, we'll understand this. Again the same thing. Say we have total number of records to be 30,000 in our employee table, and the block size is 1024 bytes as usual. Length of each record in the index file for my secondary index also will be like, say 9 bytes for my SSN and 6 bytes for pointer. Just for easy understanding, I've taken it like this. So what is the length of an index entry in my secondary index? 15 bytes. How many entries should be there in my index file, secondary index file? How many entries should be there in my secondary index file? It is 30,000 because for every value of your SSN you need an entry in your index file. So how many records you should hold? 30,000 records. So even before that we'll make up this calculation. How many index record a block can hold? A block is 1024 bytes. An index entry is 15 bytes. How many records a block can hold? It's 1024 by 15, 68 entries. We have already calculated this. But how many entries should be there in my index file? That is 30,000 entries because for every record there should be an entry in my index. So how many blocks to hold these 30,000 entries? 30,000 by 68. So how many blocks you need? 442 blocks. Because secondary index holds all the records, the number of blocks will be more. So if I do a binary search on my secondary index, binary search is possible because secondary index is ordered file. So how many blocks on an average I should access by performing a binary search? It is log 442 base 2, that is 9 blocks. That is the thing I'm going to perform on an secondary index. Plus 1, why you need that plus 1? To read the record, actual record from the block. So total number of block access here is 10 blocks. So you understood why I use this plus 1? Do you understand why I use this plus 1? You do a binary search. Say you have 442 blocks in your index file. When you do a binary search, how many blocks you're going to access on an average? 9 blocks. So you're going to go to a block. Say you have come to this block and you have found that where that actual record is. Now this is actually pointing to some other data block. 251 is here. So you access 9 block plus 1 block to actually go to that record. So it is 9 plus 1. Total number of blocks is 10 blocks. That's what is the meaning. So by using binary search on a secondary index, how many blocks you have come out with? 10 blocks. If I don't have a secondary index, what I should do? I should go with a linear search. In a linear search, how many blocks I should access? See how the performance improves here. Instead of accessing 1500 blocks, by creating an index, I reduce it to 10 blocks. So if you run some queries without creating an index, it will be running for 1 hour, 2 hours or 3 hours because it's going to do a linear search on 2 million or 3 million or data that is of several gigabytes in length. So what are the advantages of secondary index? We landed up with 10 blocks. It's better than your linear search, but not better than your primary index. Primary index ended up with 7 blocks, but this ends up with 10 blocks. And absence of secondary index will lead to linear search on the data file. The number of blocks accessed is also reduced with secondary indexing. I will end my lecture with this concept alone. What is a dense index? If you create an index wherein for every search value here, you're going to have an entry here. Is it true? For every search value, SSN is present in your index. So that kind of an index is called dense index. If only a few values are present in the index entry, it's a sparse index. So that's the difference between primary index and secondary index, dense index and a sparse index. Thank you.